Welcome to the test review for the three sections from chapters 4 and 5, 4.1 Rational Functions, 5.1 Function Composition, and 5.2 Inverse Functions. Like our other test reviews, go ahead and pause and write down the problems, then go ahead and check with the quick solutions, and then if you need to take a look at any of the worked out solutions and explanations, do so. This review is very similar to your test. It's not the exact same problems, but they're pretty similar types of problems. So if you do well on here, you should do great on the test. Good luck. Welcome to the worked out solutions. In number 1, we have a rational function f of x, and we will work through parts a through e. In part a, we want to completely factor the numerator and denominator in order to set up this problem in order to identify parts b through e. So in our numerator, what we can do is first factor out the GCF, which is 2, and so then we're left with x squared minus 4x minus 12. Our denominator, as we see, is a difference of two squares. So that'll factor into x plus 2 and x minus 2. Continuing on, in our numerator, what's left here is a quadratic trinomial with a value of 1. We have a c value of negative 12 and a b value of negative 4. Two numbers that multiply to negative 12 that add up to negative 4 are a minus 6 and a plus 2. So now our numerator is completely factored, and our denominator has been factored as well. So that is our answer to part A. Now part B is going to use part A, and so in part B, the vertical asymptote is the value of x, any value of x that makes our denominator 0 that is from a factor that doesn't cancel out. So we can see that we actually do have the x plus 2's that end up canceling out from top to bottom. That means there'll be a hole at some point, but our vertical asymptote is the value that makes what remains in the denominator equal to 0. So our vertical asymptote is what makes x minus 2 equal to 0, which is x equals positive 2. If you graphed this on Desmos, you would see that it would have a vertical asymptote at x equals 2. So that's always a good check, is to look on Desmos. For part C, seeing if we have any holes in our graph, the hole is the x value that makes the factor that canceled out equal 0. So our x value here for our hole is going to be negative 2, because if we plug negative 2 into x plus 2, it makes it 0. Now we need to find the y value. In order to find the y value, we can plug in what the function would have been at that point. So we obviously can't plug it into the x plus 2 over x plus 2. That would give us 0 over 0. So instead, we're going to plug negative 2 into what remains of our function, the stuff here that remains in orange. So we'll plug in x equals negative 2 to what remains. So that's what remains in our numerator, plugging in negative 2 for x. And in our denominator, what remains is that. So when we simplify, we'll have 2 times negative 8 in the numerator, and we'll have negative 4 in the denominator, which divides out to positive 4. So we would have a hole at negative 2 comma 4. Part D is asking about the horizontal asymptote, and in order to find a horizontal asymptote of a rational function, we need to identify the degree of the numerator, n, and the degree of the denominator, m, and our n value is 2, and our m value is also 2. So because n and m are equal, the horizontal asymptote ends up being the ratio of the lead coefficients, a over b. Our leading coefficient in the numerator is 2, and our leading coefficient in the denominator is 1. Be careful, the leading coefficient isn't always necessarily leading the way. You just have to make sure that it is the number that's in front of like the term with the degree in it. So we want to make sure it's written out so we can clearly identify what those values are. In this case, the leading coefficients do lead the way because of how it's written. So our horizontal asymptote is the horizontal line y equals 2. In part E, we want to answer the question, what x values are not in the denominator? And before, when I factored the denominator, it factored into x plus 2 and x minus 2. Therefore, the two values that are not in the domain, and I think I said denominator before, the values that are not in the domain are 2 and negative 2. So these are the two values not in our domain because they make the denominator 0. In number 2, there's a ton of different answers that you could have here, but in order to write the equation of a rational function that has a horizontal asymptote of 0, we have to make sure that the degree of the denominator m is greater than n, the degree of the numerator. So in order to have a horizontal asymptote where y equals 0, we have to make sure that n is less than m. The degree of the denominator is greater, actually. So, for example, we could have a rational function that has a degree of 3 in the denominator, and we could have a degree of 1 in the numerator. So this is just one of an infinite amount of examples, so long as the degree of your numerator is less than the degree of your denominator. For part B, in order to have no horizontal asymptote, that means we're not bounded by any horizontal line at all, and actually our function shoots off to infinity, meaning the numerator runs wild. So the degree of the numerator is actually greater than the denominator here. And so one of an infinite amount of examples, once again, could just be, let's just flip what we have in the previous example. So long as the degree of our numerator is greater than the degree of our denominator, we're totally fine. And then in part C, to have a horizontal asymptote of 1/2, our n and our m values need to equal each other, and the ratio of our leading coefficients needs to be 1/2. Well, there's an infinite amount of ways to get 1/2. I'll pick a fun way. I'll do 13 over 26. That's a fun way. So we'll have 13x plus 4 over 26x. We'll do something weird. So again, there's an infinite amount of rational functions that could work, so long as n equals m. So here our degrees are both 1, so n and m are both 1, and the ratio of our leading coefficients is 1/2. 13 over 26 would simplify to 1 over 2. In number 3, we want to sketch the graph of a function that is 1-to-1. In order for a function to be 1-to-1, it needs to pass not only the vertical line test, ensuring that it's actually a function, but also the horizontal line test to ensure that its inverse is also a function. So the sketch of a 1-to-1 function can be simple. It can just be linear, like that. That clearly passes both vertical and horizontal line tests. Our function could also look a little more exciting, and it could look like something like this, like the square root function. So long as your graph passes both the vertical and horizontal line tests, meaning that if you drew any vertical or horizontal lines through it, it would only hit your graph one time. That means that you have a 1-to-1 function. In number 4, we have a pretty simple linear function f of x, and we want to find the inverse. In order to find the inverse of a function, what you need to do is swap x and y. So I haven't done anything yet. I just rewrote f of x as y. So in order to find the inverse, which I'll do in blue, I want to swap x and y. Then we want to resolve for y. So we have y equals x minus 3, and therefore our inverse function, replacing y with f inverse, which is what it is x minus 3. So it's not quite its own inverse, but with a linear function like this, it's not too difficult to find the inverse by swapping x and y and solving for y. In number 5, we want to again find the inverse functions. So what we need to do is swap x and y and solve for y. So in part A, all I'm going to do first is just replace f of x with y. I have not yet swapped x and y to find the inverse. In the next step, in blue, I will find the inverse. So I'll swap x and y. So now we technically have the inverse function, but in order to write it as a function, f inverse of x, we need to solve for y. So what we'll do is add 7 to both sides. And then because y is in a square root, we want to square both sides. Squaring and square rooting will cancel each other out, so we're left with y plus 1. Then on the left-hand side, we're left with x plus 7 quantity squared. When we multiply this out, we'll get x squared plus 14x plus 49. Then I want to subtract 1 from both sides. So we'll have y equals x squared plus 14x plus 48. We can replace y with f inverse and write it fancy to get this quadratic equation, which is, in fact, our inverse function. In part B, we're going to do the exact same thing. So my first step is just simply replacing f of x with y. I have not found the inverse yet. Finding the inverse means swapping x and y, so we'll have x equals 4 over y plus 2. So I've technically found the inverse, but now it's not in terms of x, which we want. We want y equals. So I'm going to multiply both sides by y plus 2, and or, cross multiplying. That's essentially what I'm doing. So on this side, I'm going to distribute my x through. So we'll have xy plus 2x equals 4. Solving for y, I'm going to subtract 2x from both sides and then divide by x on both sides. So y, our inverse, equals 4 minus 2x all over x. We can replace y with what it is, f inverse of x, and we have found our inverse function. For this problem, we have something that I entirely made up, so this is not the population of deer in Henrico County, but it could be. It works out okay. T is the number of months since January of 2021. And in part A, we want to find and interpret P of 12. So this just means we are finding the population of deer, extensively predicting the population of deer for January of 2022, 12 months after this date. So we want to obviously round it to the nearest whole number because our output is number of deer. So I just plugged in 12. Really, I would recommend just using your calculator, just plugging it all in and not even doing this much work. But I got 319.6, so rounding to the nearest whole number technically should be 320 deer. I would assume there's probably a lot more deer than that in Henrico County, but it's a decent estimate. All right, we want to interpret this. So to interpret it just means to write a statement about what it means. So this is what we're writing our statement about. P of 12 is approximately 320. So this just means that after 12 months, the population of deer is approximately 320 deer. Now you could also say in January of 2022, since we know when this exactly will be. So as long as you have these two numbers mentioned, or as long as you say in January of 2022, some time frame, and you give the approximately 320 deer, you have interpreted this correctly. In part B, we want to know when will the deer population be 330? And so we are looking for T, and we know P of T, the population. So we're going to replace P of T with 330. Then what we can do is cross multiply. And when we cross multiply, we're going to have 1 times 680 times T minus 0.25. So we'll end up getting 680 times T minus 0.25. So I'm going to distribute that 680 through. Here's some real-time math. 680 times 0.25 is 170. When we cross multiply, we put an equal sign. And so over here, I'm going to again distribute the 330 through. 330 times 2 is 660. T plus 330. So we have cross multiplied. Now we want to solve for T. So I'm going to subtract 660T from both sides. That leaves only 20T on the left-hand side. Then I'm going to add 170 to both sides. When we add 170, here it obviously cancels, and over here we'll have 500. Then we want to divide both sides by 20. When we do that, we're doing 50 divided by 2, which is 25. So it looks like 25 months after January of 2021. So that is 2 years and 1 month. So it's technically t equals 25 months, but it is asking when. So when is that? It's going to be February of 2023. Cool. I wonder if we're right. Part C is asking us, as t approaches infinity, what does p of t approach? This is a sneaky way, or just an alternate way, of asking what is the horizontal asymptote. And in order to find the horizontal asymptote, what we want to do is make sure that our numerator is like multiplied out. So we had 680t minus 170 when we distribute the 680 through, over 2t plus 1. So our rules for horizontal asymptote are to find n and m, the degree of both the numerator and the denominator respectively. They're both 1. Since our degrees of top and bottom are equal, we take the ratio of the leading coefficient to find our horizontal asymptote. Our horizontal asymptote is 680 over 2, and 680 divided by 2 is 340. This just means that that is what our graph of our function is going to level out to as t gets very large. If you plugged in an extremely large value of t, which is kind of an alternate way to do this, if you plugged in, you could just use your calculator or the Desmos like table function. If you plugged in 100, 200, 1,000, you would get output values that approach 340 and would ultimately round to 340, even though technically we never quite get there. So that just means that the population of deer is going to approach or level out to about 340 deer after a while. Okay, I love these problems. This is function composition, section 5.1. We want to find fog and goff, f of g of x and g of f of x. In part A, we want to find f of g of x. And so we're finding f of our g of x function, x squared minus 3x plus 10. Oh my. Want to fit that all in there. So we're finding f of this function. That means we want to plug this g of x function in to the f of x function. So 2 times this guy here, which means we'll have to distribute the 2, and then at the very end we still have that minus 5. So distributing our 2 gives us 2x squared minus 6x plus 20, and then we have a minus 5 at the end still. So combining like terms, we'll have 2x squared minus 6x plus 15. In part B, we want to find g of f of x. So we're finding g of 2x minus 5. So everywhere in g that there's an x, we want to plug in 2x minus 5. So we're going to first have to square it, then distribute through a negative 3, and then at the very end, add 10. To square 2x minus 5 means to multiply it by itself. So if you need to write it out and FOIL it out, feel free. The quick way to do this is to square the first term. So we'll have 4x squared. Leave a space and square the last term, plus 25. Then for that inside piece, the o and the I of the FOIL, they're the same, so what we'll do is we'll multiply 2x times minus 5 and get negative 10x, then double it. So we'll have negative 20x for our inside term. Then we'll distribute our minus 3 through, careful with that negative, and add the 10 at the end. Combining some like terms, we only have one quadratic term. We have a minus 20x and a minus 6x to combine to minus 26x. Then we have a 25 plus 15 plus another 10. So it's 25 plus 25, which is plus 50. Problem 8 is function composition again, except we're plugging in numerical values, so we will get a numerical output. In part A, we want to find f of h of 26. So we're finding f of h of 26. So the first thing we want to do is find h of 26. H of 26 is plugging 26 into the h of x function, so we'll have the square root of 26 minus 1, which is the square root of 25, which is 5. So we're essentially then finding f of 5. F of 5 is 2 times 5 squared. So 2 times 25 is 50. For part B, we're finding h of f of negative 1. And the first thing we want to do is find f of negative 1. To find f of negative 1, I'm going to plug negative 1 into the f function and worry about PEMDAS, so make sure we're squaring first. So we'll have 2 times 1, since negative 1 squared is 1, which is 2. So that means we're really finding h of 2. Finding h of 2 means taking the square root of 2 minus 1. The square root of 1 is 1. Here are the quick solutions. Problems 1 through 5. And problems 6 through 8. I'm not going to say good luck because you make your own luck through hard work and preparation, but have fun on your test.